Hi, everyone. So this is part 2. So I believe this is it's going to be page 13. So this is part 2. This is page 13. And what I want to talk about is thermodynamic potentials and different ensembles. Now, I realize the video quality is really bad. So I'm going to share, I took pictures of the notes so that when you watch the video, you can simultaneously follow the high quality picture of the notes. Sorry, I don't have an iPad. I will try to get one, but probably not until the end of the semester. Okay, so this is thermodynamic potentials and different ensembles. So this is just stepping back, bird's eye view, what's going on. So in attempting to release a constraint of constant energy that we ran into, we introduced the idea of a bath, right? So you have at first we looked at the energy reservoir at temperature T, or reservoir, that can exchange energy into or out of the system, okay? Okay, this is better. This is probably much better. And one might ask how this can possibly be useful for predicting properties of an isolated system, which is what we were really trying to calculate when we ran into the constraint problem. In an isolated system, the energy is fixed. However, when the system is large, fluctuations into and out of the system, fluctuations of energy are small, let's say negligible. So while the energy is technically not fixed, it is essentially fixed. So this is how we're circumventing the constraint in calculations, right? You see the calculations are in this type of setup, with partition functions and all, they don't run into a constraint because technically there is no more constraint. So while we're circumventing the constraint in calculations, we are making predictions for essentially a fixed energy system. So it's like a clever trick. And then, of course, there are circumstances where the bath really is natural. You don't always have an isolated system. For instance, we may be interested in fluctuations of a molecule, which isn't a large system. So the energy fluctuations are not small, but it really is in a constant temperature environment from which it can borrow arbitrary amounts of, or some amounts of energy, or as much as it can absorb. So there are physical situations that don't correspond to closed systems. They're called open systems. That's very common, right? So especially with quantum systems, there's a whole field called open quantum systems. And then that really does correspond to this, okay? So what I said, this is a video, so I'm not going to write things on the board. You can take notes from whatever you want to write down for what I said. So except for an isolated system, we've looked at two examples, the one with energy bath and the other with energy and particle bath. And in both cases, there's a partition function for each type of a bath. So each type of bath, there's a corresponding partition function. So this situation has a partition function Z, and this is energy and particle bath. This has a partition function, the grand canonical partition function, the script Z. In both cases, we can group terms based on energy using the degeneracy factor omega. And we find that as n goes to infinity, there is one dominant energy. So you can think of this as in phase space, a system can exist on multiple energy shells, but it's going to spend a vast amount of time on one particular energy shell. That's a little bit like when you study in quantum mechanics, when you study electron distribution around the nucleus and hydrogen atom, while electron is most likely to be at the nucleus and in the ground state, the probability falls off exponentially. When you study the radius where the electron is most likely to be found, there's some optimal radius. Because while the distribution falls off with radius, there are more spots, there are more locations with larger radius. So you have something like r squared times e to the minus some constant times r, and there's an optimal radius. The same thing happens here, except that it's a very sharply peaked function. Okay, so we group terms based on energy in calculating these kinds of things. At large n, there's one dominant energy. And if it involves also exchange of particles, then also one dominant number of particles. And so we get things like z is approximately minus beta e star minus t s at e star n star minus mu n star, or things like e to the minus beta e star minus s ts at e star. And similar for other types of baths. Sorry. And similar expressions for other types of baths. So I will have more words to say about that in a minute. So to each type of partition function, there corresponds a thermodynamic potential defined as minus kt log of the partition function. So once before I circle this, for each type of partition function, there corresponds something called a thermodynamic potential defined as minus kt times log of the partition function. So to z, there's the grand canonical partition function minus kt log of z. For regular partition function, there's the free energy I forgot what did I call it? I called it, I think it's called Landau potential. Yeah, Landau potential. Oh, for this, you have minus kt log of z. This is called Helmholtz free energy, at least in America, in the West in general. And you have other types of ensembles with corresponding to other types of baths. They have their own partition functions, and they have their own thermodynamic potentials. And because of approximations such as this, minus KT times log of Z is going to be just this. So approximations such as these thermodynamic potentials can be written in the form which we just write like that. Remember, star means the optimal value, the optimal energy, that's by far the most likely energy, by far the most likely energy is basically the same as the average energy, which is the same as like the energy. Like it's the only energy that system is going to have, except for a teeny tiny fluctuation. So we just write it like this. Or for canonical bath, we write, which we can write like this. Okay. So the most probable values are replaced by mean values, which are essentially the only values, but because fluctuations are so narrow for large systems. And if n is not large, then we can define the corresponding potential from this. It's not a fluctuating quantity. And then we will just not use these formulas. They're not useful for small systems. But for large systems, where you do have the most dominant term in these sums, for large systems where you do have the most dominant term in the sums, these partition functions can be approximated like this. And in that case, these thermodynamic potentials, like the grand canonical potential or the Helmholtz free energy, are basically given in forms like these, in terms of other thermodynamic quantities like energy, number of particles, entropy, temperature, and so on. So these are called thermodynamic potentials. And thermodynamic potentials are functions of variables that are naturally fixed in each situation. So you see U, well, actually here, Z, for example, let's say you have a canonical bath, it's the Z will end up being a function of T, as well as number of particles in the system and volume of the system. And again, there are generalizations. So if it's a magnetic system, then instead of volume, we have magnetization. If there's if it's a electrically polarizable system, then it would be polarizability, and so on. So by V could be literally a volume, or it could be a placeholder for other types of variables. And so you see Z is Z is a function of Tn and V, and so F is a function of Tn and V. Now here you have to realize that U is a function of Tn and V, and S, that's a function of U, which is a function of Tn and V. So sorry, this is supposed to be F. Sorry, Helmholtz free energy, not Z. My apology. Okay, I'm glad I caught it. So in any case, so you have thermodynamic potentials. They're functions of variables that are naturally fixed in each situation, situation. So in the canonical situation, you have T and V. So Helmholtz free energy is a function of T and V. And if you have a grand canonical bath, that's the bath's property of temperature and chemical potential, then n is fixed, then the grand canonical potential is a function of T mu and sorry, this is V T mu and V. Okay. Okay. And V. And the temperature of the system can fluctuate, but the temperature of the bath is fixed. So this is really T of the bath. Again, if the system is large, the temperature of the system equals the temperature of the bath. If the system is small, you still have partition function, you still have free energy, and it's still a function of T and V, except that by T, we mean T of the bath, which is fixed. Okay, so in each case, you have these natural variables. And these natural variables are fixed. For isolated system, the thermodynamic potential is entropy. I should mention that for isolated system, S is the thermodynamic potential. And in that case, what are the natural variables? What's fixed? Well, the energy is fixed, number of particles is fixed, and volume is fixed. Or other thermodynamic variables, like magnetization. You saw when the system is closed, number of spins up minus number of spins down is fixed. So magnetization is fixed. It's not a fluctuating quantity. You can also rewrite this. You can instead, so S is some function of E and V, and sometimes we rewrite E as a function of S, N, and V. This is also a way to describe isolated systems. And we saw that thermodynamic potentials provide a key to thermodynamics. How do we do that? So first you can form a total differential and compare what it is based on calculus. So df equals df dx partial f partial x dx plus partial f partial y dy plus partial f partial z dz. In this case, the total differential of the Helmholtz free energy is df equals partial f partial t dt plus partial f partial n dn plus partial f partial v dv. And we obtain relationships between various thermodynamic quantities and derivatives of thermodynamic potentials, because you also have definitions such as 1 over t is partial s partial e, p over t is partial f partial v, and so on. And so you get, look over your notes, see how we got thermodynamic identities. For example, minus s dt minus p dv plus mu dn. And when we look at the next thermodynamic potential, for example, this one, you have things like, you take a total differential of this, it will be du minus mu dn minus n d mu. We did it today. Minus t ds minus s dt. And we know what ds is from our study of isolated system. And then when we plug things in, we get, on the one hand, something like this, and on the other hand, this is partial F, partial T. This is partial F, partial V at fixed T and N. This is at fixed V and N. And this is going to be partial F, partial N at fixed T and V. So on the one hand, you can write a total differential based on what it is in calculus. On the other hand, you can use these forms. We use these forms of thermodynamic potentials to form a total differential to get something that looks like that. And then by comparing with the calculus form, you can read off what each derivative means. And so that's how you get your P to thermodynamics. So then if you then the procedure is you calculate partition function, you take the log, multiply by minus KT, that's your corresponding thermodynamic potential, and then various derivatives of the thermodynamic potential give you various thermodynamic quantities. So partial F partial T equals minus S, or minus partial F partial T equals S, minus partial F partial V equals pressure, and so on. Right? So this is how you get P to thermodynamics. Like I said, there are other types of baths with their own corresponding thermodynamic potentials. I want to make sure you're able to view this page, right? So this is the page. Hopefully you could see this, okay? And again, I'm sharing these pages. I'm going to share these pages. There are other types of thermodynamic. There are other types of baths with corresponding thermodynamic potentials. For example, you can have an energy bath and a volume bath. So instead of exchanging particles, a system can exchange volume. Right? So the system can exchange energy, the system can exchange volume. And such a bath, what's fixed for such a bath? So pause the video and think about it. Well, T and P. N is fixed in the system. What's the name of this thermodynamic potential? This is called Gibbs free energy. Not to be confused with Gibbs distribution, the script Z, which corresponds to the grand canonical situation with the exchange of particles and energy. So this is called Gibbs free energy, G, and it's a function of T, N, and P. So these are the natural variables for this type of situation. Just a second. This is supposed to be 15. So this is supposed to be 16. Okay, 16. Okay. You can also have just a volume bath. So here your system, this is a little bit tricky. It can exchange a volume with the environment. This gives rise to enthalpy. The thermodynamic potential here is called enthalpy. What is this a function of? So if you can exchange volume, okay, energy also enters through the bath, but how does it enter? It enters by performing mechanical work. So imagine you have a piston and then you can push piston into and out. So the bath here performs mechanical work, and by performing mechanical work, it adds or removes energy into the system. We'll discuss at the next lecture this idea. In all of the baths that we have considered so far, there is no change in volume, so there is no mechanical work. And the energy enters by means of heat. So at the next lecture, we'll discuss two ways of changing energy of the system. When you have this type of bath, energy enters by means of work. When energy enters by means of work, as long as you do that work sufficiently slowly, and that's how baths operate. They're incremental changes in the volume. You don't have a rapid change. You don't have some kind of an external force. This is just exchanging, free exchange of volume with the bath. So the system basically is always near equilibrium with the bath. So the system is always near equilibrium. In that situation, the entropy of the system stays constant. The entropy can only enter through heat. In this case, energy enters as work, so the entropy of the system stays constant. So this is a bath at pressure P, so it's a function of P and an S. It's an unusual bath. We will not talk about it. So, but in all other circumstances that we saw, the baths in all other examples should really be called heat baths. So here the energy enters not by means of work, but by means of heat. Heat is a way to transfer energy without doing any mechanical work. And so is this. This should really be called heat bath. This is a heat and particle bath. This is a heat and pressure bath. Oh, sorry, heat and volume bath. Okay, so these are just two other examples. And you might say, well, I'm getting confused. When do we use whichever bath? So different baths correspond to different physical situations, and they have different applications. Enthalpy, this type of thermodynamic potential, is useful in chemistry, and it gives heat produced in chemical reactions, whereas Gibbs free energy is useful in studies of phase equilibria and also sometimes in chemistry. I don't expect you to be an expert in knowing when to use whichever thermodynamic potential. This is just more like a museum tour, so that when you hear things like Gibbs free energy or enthalpy of Helmholtz free energy, you understand what it is. These are just different keys to thermodynamics that correspond to different physical situations. When we had a problem like the substrate problem, it was clear from the context what is being exchanged. Energy is being exchanged because when a particle adsorbs on the surface, there's an energy cost or energy benefit to that epsilon, and particles are being exchanged. So the ideal gas bath above the substrate is clearly this type of bath. So clearly the right kind of calculation to do in that circumstance was to calculate the grand canonical partition function and calculate grand canonical potential, or Landau potential. When you have a molecule being jiggled by the thermal bath, the number of particles stays constant. The volume is not even a relevant variable there, and it's just exchanging energy with the environment. Then the right kind of thermodynamic potential is the Helmholtz free energy. And the right kind of partition function to calculate is the regular canonical partition function. So it's not such a mysterious question. We just simply haven't studied the situations corresponding to Gibbs free energy or enthalpy, and we will not, but just so that in the future, when you hear these terms, you understand that these are just types of thermodynamic potentials. All of the potentials except entropy, what they give you is they give you the energy that can be extracted for use. In other words, the amount of useful work, or equivalently, the work needed to put the system together. I mentioned it once when I explained where the terminology Gibbs, Helmholtz free energy comes from. Why is it called free? It's actually kind of a not an ideal normer, not the ideal name, but for example, when we looked at Helmholtz free energy, E minus Ts, let's look at this. What this gives you the energy required to put together a system at constant temperature. And that energy, the energy that a user, the energy that you have to provide is not E, but it's E minus Ts. Why E minus Ts? Because Ts is how much energy is provided spontaneously by means of heat from the bath. And so the amount of energy that you have to provide on top of that is really the difference between the total energy of the total energy in the system and how much energy is provided for free from the bath. And so the amount of useful energy that you can extract back, you cannot extract all of this. Because if you do, in other words, if you disassemble the system and convert the entire energy into work, then you've basically destroyed entropy. Because to create the system, we'll discuss more of this the next class. But you see, when heat enters from the bath, entropy enters from the bath. So entropy enters from the bath. And now you say, okay, I'm going to just disassemble the whole system and extract the entirety of energy. You've just converted entropy. You've just destroyed entropy, basically. That's not allowed by second law of thermodynamics. So whatever energy you put, namely this difference, you can get back, but you cannot get all of this energy. So again, to put the system together, some of the energy is provided from the bath. You have to provide the difference between the total energy content and how much heat is provided by the bath. So when you want to extract useful work back, the total amount that you can get back is the same amount that you put in, namely E minus Ts. You cannot get the whole energy back because then you're cheating. You destroying entropy, which is not allowed by second law of thermodynamics. What I said will become more clear after next lecture. Thermodynamic potentials also tell us about probabilities of fluctuations. Okay, so thermodynamic. So first of all, let me just thermodynamic potentials tell basically give the energy required to put the system together, put n atoms into the box, right? Compress atoms into a box of volume V, or extract. So basically, give I should say work, or extract work back from the system. And so one textbook that I read, it says it should not be called free energy. what's provided for free really is this. That's free energy. That really the right name would be this comes for free. The work that you do to put the system together, you pay. That's the energy you have to expand. And that's the energy you can get back. Maybe that's why they called it free. Next use of thermodynamic potentials is, let me start on the next page. Thermodynamic potentials also tell us about probabilities of fluctuation. What do I mean by that? So in our discussion of entropy, we noted that during a fluctuation of a closed system, entropy decreases. So the entropy reaches maximal value when the system reaches the most probable macro state. And therefore, during a fluctuation of a closed system, the entropy decreases. System goes to a macro state that corresponds to the suboptimal number of microstates. So for example, when the air in a room is distributed unevenly, the entropy of such an unusual macro state is smaller than when it is distributed in the most likely way, which is basically the even distribution, which is the equilibrium distribution, right? So when we have some kind of a uneven density, this corresponds to entropy S1 versus the even density. This is the equilibrium entropy, and S1 is less than S equilibrium. So S as a function of distribution of internal variables, internal macro variables, is maximized in equilibrium. We've studied that in the context of two subsystems, each of which is in equilibrium, but it doesn't have to be two. It could be arbitrary number of subsystems, arbitrary distribution of energy within the system. Okay? And the same idea generalizes to all other situations of contact with various baths. With the only difference is that in all of those cases, the corresponding thermodynamic potential will take on the minimal value with respect to internal fluctuations rather than the maximal value. As entropy is unique. Entropy is maximized at equilibrium. All other thermodynamic potentials are minimized at equilibrium. So let's say there is a system in contact with the energy bath, canonical situation. This is your energy bath, or as I said, it really should be called heat bath. So this is the system, this is the bath. And let's say we prepared a macroscopic fluctuation by making some kind of a disturbance inside the system. It could be a disturbance inside the system, or we can pump more energy into the system that's equilibrium value, or remove energy so that the energy content of the system is smaller than the E star, smaller than the equilibrium value. Or we could do some unusual distribution of energy inside, right? So you have a box of gas, it's in contact with the bath, and I move particles around so that you have like high density, just like I said, high density of the gas in one corner of the room. So let's say we created such a disturbance while N, V, and the temperature are held fixed, right? So create a disturbance at fixed natural variables. I mentioned that's when we're talking about relaxation of fluctuations, these are fluctuations of all variables that can vary while the natural variables are fixed. So what are the variable? T of the bath, number of particles, and volume in this particular situation, right? And then you watch the fluctuation relax. Okay, fluctuation relaxes. You can have a fluctuation of temperature of the system, but T of the bath is fixed. Okay, you make a disturbance to create a fluctuation, or it is a spontaneous fluctuation. We can literally do work to create that fluctuation, or you just wait long enough and you see molecules in the room collect in a corner. It could be a spontaneous fluctuation. And then thermodynamic potential decreases, again, except for entropy, which increases in a relaxation of this type of a macroscopic fluctuation to equilibrium, while the appropriate natural variables are held fixed. Okay, so thermodynamic potential decreases except S. So if you have a closed system, then entropy increases in a relaxation of such a macroscopic fluctuation with appropriate natural variables fixed. So temperature of the system can fluctuate, but temperature of the bath is fixed. And the thermodynamic potential is minimum except for S, which is maximum, with respect to such fluctuations in equilibrium, right? We're talking about macroscopic fluctuations with fixed natural variables, okay? Moreover, the difference in the thermodynamic potential between the value it takes on in a fluctuation, that's why I'm saying it has to be a macroscopic fluctuation, so we can calculate the thermodynamic potential for such a fluctuation. The difference between that value of the thermodynamic potential and the minimal value, given the fixed natural variables, actually tells us the probability of such a fluctuation. So the probability of a macroscopic fluctuation at fixed natural variables is given by e to the minus beta times delta potential. I mean, thermodynamic potential. Or again, if it's entropy, e to the delta S over K Boltzmann for entropy of a closed system. I'm not going to prove this, but this you can see where this comes from, because e to the delta S over KB is just the ratio of multiplicities. Okay. So this is kind of obvious. This requires some, proving. But I have to say one thing though. This statement, it still assumes that equilibrium statistical mechanics applies. So let's say if a system is driven at a rate exceeding the rate at which it's able to explore its phase space, then not only do you, well, then the concept of entropy and other thermodynamic potentials loses its meaning. With entropy, for example, entropy has to do with the number of accessible microstates, but that quantity only makes a physical sense if the system has time to explore them. So when the system is driven, you could, for example, have a closed system that's internally driven. If you have an open system, then the thermodynamic potential would not be the entropy, but it could be like, for example, Helmholtz free energy, which is U minus TS. So entropy is still involved here. So if the system is driven at a rate exceeding the rate at which the system is able to explore its phase space, then the concepts of entropy and all other thermodynamic potentials, they lose their meaning. And the probabilities of fluctuations are no longer given by these expressions. Then we enter the realm of non-equilibrium statistical mechanics. You can, calculation of probabilities of fluctuations become a very, very interesting problem, but it's not given basically by counting states. You see, when you dress this down enough, this is just counting states. We're saying how much less likely some unusual macro state than the equilibrium macro state. Well, it means what's the ratio of the number of microstates in the unusual macro state than in the most likely macro state. This is really just counting argument. But if you have a driven system, basically, for example, in the situation of closed system, fundamental hypothesis doesn't work anymore. So probabilities no longer boil down to counting microstates. So let's say you have a cell, biological cell, and inside the cell you have molecular motors, right? And let's say the cell is basically a closed system, right, on a sufficiently small time scale. You have a system that inside undergoes energy transfer processes. It's driven from the inside. And you want to calculate probability of some fluctuation, probability probability of some kind of fluctuation of some structure. Probability that a molecular motor runs at an unusually large speed, for example. Typical speed of a molecular motor is like 1 micrometer per second when it walks on microtubules. But sometimes it could absorb unusually large number of ATPs and it could run unusually fast. Can you use this methodology? The answer is no. You cannot use equilibrium statistical mechanics because it's an energy conversion process. It's not an equilibrium. It's not within the realm of equilibrium statistical physics. But in any case, that's kind of like a side remark. And that's all I wanted to say. I want to get a little head start on the next lecture. And this is about heat, work, and second law. Standard topic presented in any thermodynamics class, and I think it would be wrong to not, to sidestep. The first thing to get across is the idea that energy content of a system can be changed in two ways. In the first case, the energy content of a system can be changed while the external parameters, such as volume, length, magnetization, do not vary in time. And if the system is quantum, that means all the entire energy structure, all the energy levels and degeneracies of the system are fixed. In this situation, the transfer of energy into and out of the system is called heat. You can just think of it as a definition. It's universally denoted by letter Q. Okay, so external parameters. So this means there's no work involved, because when you do work on the system, you have to change some external parameter. You have to change the volume by applying pressure. You have to change magnetization by cranking up magnetic field. You have to change polarization by cranking up electric field. So you see, you have these two conjugate variables: pressure, volume, magnetization, magnetic field, polarization, electric field. If you don't vary them on time, you're not doing work in any way. And a situation when energy enters into and out of the system, not by means of work, is called heat. Okay, so energy transfer process is called heat. Universally, it's denoted by letter Q. I mean, I've never seen anyone use any other letter for Q. Q bigger than 0 means energy enters the system by means of heat or via heat. Q less than 0, energy leaves by means of heat. In discussing our energy baths or energy plus particle bath, the energy added into or out of the systems was in fact heat. So both types of baths that we spent a lot of time on, when energy enters or leaves the system, this is the energy bath, this is the energy and particle bath. Here, and energy enters. These are both heat baths. So this really should be called heat bath. And this should be called heat and particle bath. You have a system in contact with the reservoir, the volume of the system is fixed. So the energy transfer process is not work. And when it's not work, it's called heat. If a system is thermally insulated, no heat can enter or leave the system. Okay. We can also transfer energy into and out of the system, even if it is thermally insulated, by a variation of external parameters. Okay, so thermal insulation, no heat. If and is if a system is thermally insulated, energy can enter, leave due to a variation of external parameters. Quantum systems make it especially clear how that happens. Consider some energy structure. Of a quantum system. I'm just going to make something up. So you have a ground state energy, and then you have a degenerate second level, and then you have triply degenerate third level, and then maybe a fourth level. And let's say I stretch the system, increase one side or something like that. All the levels will shift, right? So your ground state energy level changes. These energy levels maybe become triply degenerate. These energy levels shift, and this energy level shifts. Okay, so you change some parameter, length, volume, or something else. Energy levels shift. And for generality, I also drew different degeneracies. So a variation of external parameters changes this energy structure. And if a system is located, say, at one level, and the change is sufficiently slow, it will stay at the same level, but typically it will now have different energy. So let's say you have a system in the ground state, and you lower the energy of the ground state. Now the energy of the system has changed. So this shows that variation of external parameters clearly can change the energy of the system. And if the process is sufficiently fast, then the system might also make a transition. You study that, for example, in time-dependent perturbation theory. If the change in the variation is sufficiently fast, then the system can end up at the second level or the third level or something like that. It can make a transition. In any case, such energy transfer processes by means of heat, but by means of change of external parameters, very temporal variation of external parameters, are called work. In general, if a system is coupled to the environment and its external parameters, such as volume change, there's going to be both heat and work involved. So we will continue with this discussion on Tuesday. we will come up with some sort of expressions for the amount of heat and the amount of work involved in a particular energy transfer process. We will discuss the idea that heat must accompany entropy change in the bath and in the system. But work does not involve any entropy change. We will discuss quasi-static processes when the system is always close to equilibrium. Bath is always assumed to be close to equilibrium. And fast processes when that isn't the case. And then we'll make a few more fundamental statements. So once again, we will return to the subject of entropy from a purely thermodynamic perspective. And in the lecture following that, we will explore the connection between, we will take a different, take a different look at entropy from the perspective of information. So these are wildly different ideas. The entropy from thermodynamics has to do with, how much work can you extract from a heat engine? Entropy, turns out, also has the meaning of information. It has an information connection with information, and it's remarkable that these things are related. The same entropy that you use in order to calculate the amount of work that you can extract from the heat engine, turns out there's an information theoretic underpinning to that entropy. It's the same entropy. In any case, thank you for bearing with me. I will share the PDFs of these notes. Both parts of the lecture will be uploaded to YouTube. And then I will see you on Tuesday. We'll continue our discussion on Tuesday. Would like to start on quantum systems on Thursday. Then we have 6 lectures left, if we don't count the exam. And we'll cover as much as we can in those 6 lectures. Okay, thank you, bye.